Hello, welcome back. In the last video, we discussed about Euclid's division algorithm, and today we are going to discuss about fundamental theorem of arithmetic. While division algorithm says about the division of integers, fundamental theorem of arithmetic says about the multiplication of integers. The fundamental theorem of arithmetic says that every composite number can be expressed as product of primes. Hope all you know about prime numbers and composite numbers. Prime numbers are the numbers that have only two factors, one and that number itself. And composite numbers are the numbers that have more than two factors. Example, 2 is a prime number. The only factors of 2 are 1 and 2. 3, the only factors 1 and 3. 5, 7, 11, 13, 17, 23, etc. And composite numbers 4. The factors are 1, 2, 4. 6. The factors are 1, 2, 3, 6. 8. Factors are 1, 2, 4, 8. 9. Factors are 1, 3, 9. 10. Factors are 1, 2, 5, 10, etc. Fundamental theorem of arithmetic says that every composite number can be expressed as product of primes. Say 4 is equal to 2 into 2. 6 is equal to 2 into 3. 8 can be written as 2 into 2 into 2, the prime factorization. Take 12 is equal to 2 into 2 into 3. Take 18 is equal to 2 into 3 into 3. Here 4 is equal to 2 square, 8 is equal to 2 cube. 12 can be written as 2 square into 3. 18 is equal to 2 into 3 square. Or we can say every composite number can be expressed as the product of primes or product of powers of primes. Also, this factorization is unique apart from the order in which the prime factors occurs. Here see, the only prime factors involved in the factorization of 18 are 2 and 3. No other prime factor. The order can be changed. That is, we can write 18 as 3 into 2 into 3 or 3 into 3 into 2. Only the prime factorization is unique. Non-prime factorization need not be unique. See, 18 can be written as 18 is equal to 1 into 18, 2 into 9, 3 into 6, etc. The non-prime factorization need not be unique, but the prime factorization is always unique. Theorem, fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. I have already said that a non-prime factorization need not be unique. That is, the prime factorization of a natural number is unique except for the order of its factors. Hope you understand this concept. We can see an example. Consider the number 4 raised to n, where n is a natural number. Check whether there is any value of n for which 4 raised to n ends with the digit 0. Given a number 4 raised to n, we have to check whether there is any value of n for which it ends with the digit 0. The numbers that end with the digit 0 are 10, 20, 30, 40, 50, etc., 100, 110, 120, etc. All the numbers that ends with the digit 0 have the factor 5, or all the numbers are divisible by 5. So, if 4 raised to n ends with the digit 0, it should be divisible by 5. See, 4 raised to n can be written as 2 raised to 2n. Here, this is the prime factorization of 4 raised to n. By uniqueness of prime factorization, or by fundamental theorem of arithmetic, the prime factorization is unique. So the only prime factor involved in the factorization is 2. So 5 cannot be a factor of 4 raised to n. Hence, there is no number n for which 4 raised to n ends with the digit 0. See, if the number 4 raised to n for any n were to end with 0, then it would be divisible by 5. That is, prime factorization of 4 raised to n would contain the prime 5. This is a prime number, so the prime factorization should contain this number. This is not possible because 4 raised to n is equal to 2 raised to 2 raised to n. So the only prime in the factorization of 4 raised to n is 2, because the prime factorization is unique by fundamental theorem of arithmetic. So by uniqueness of fundamental theorem of arithmetic, there are no other primes in the factorization of 4 raised to n. So there is no natural number n for which 4 raised to n ends with the digit 0. Hence the answer. Next, we can recall the prime factorization method to find LCM and HCF that you have studied in your early classes. Before that, we can see HCF and LCM. We have already seen HCF in the last video. That is, to find the HCF of two numbers, list the factors of two numbers and then find out the common factor and then find the highest among those common factors. To find the LCM of two numbers, we have to list the common multiples and find the least among the common multiples. See, LCM of 2 and 3. Common multiple, we have to see the multiple first. The multiples of 2 are 2, 4, 6, 8, 10, 12, etc. And the multiple of 3 are 3, 6, 9, 12, 15, etc. Here the common multiples are 6, 12, and so on. Here the least common multiple is 6. Therefore, LCM of 2 and 3 is equal to 6. Find the LCM and HCF of 6 and 20 by prime factorization method. Now we can see the prime factorization of 6. 6 is equal to 2 into 3. 20 is equal to 2 into 2 into 5. Just 2 square into 5. HCF of 6 and 20 is equal to, the common factors are 2 only. Therefore, highest common factor is 2 itself. And LCM. LCM is the least common multiple. So to find the least common multiple, take the common factor once. Then it becomes 2 into 3 into, need not take this 2 again, 2 into 5, which is equal to 2 square into 3 into 5. Next, consider the example 12 and 18. Find the HCF and LCM of 12 and 18. The prime factorization of 12 is 2 into 2 into 3. And the prime factorization of 18 is 2 into 3 into 3. Here it is equal to 2 square into 3. 18 is equal to 2 into 3 square. Here the common factors are 2 and 3. Therefore, highest common factors are 2 and 3. Therefore, highest common factor is 2 into 3. 2 into 3. And LCM, least common multiple. So, consider 2 ones and 3 ones. 2 into 2 into, here 3 take once, 3 into, here again a 3, 3, which is equal to 2 square into 3 square. We can see another example. Find the HCF and LCM of 24 and 180. Prime factorization of 24 is 2 into 2 into 3 into 2. And prime factorization of 180 is, we can check 180, the least prime factor is 2. 90. Again 2, 45. Again 3, 50. Again 3, 5. Therefore, the prime factorization is 2 into 2 into 3 into 3 into 5. Here it's which is equal to 2 cube into 3. Here which is equal to 2 square into 3 square into 5. Here the common factors are 2, 2 times and 3. Therefore, HCF, highest common factor is product 2 into 2 into 3, which is equal to 2 square into 3. And LCM is equal to, consider 2 ones, again consider it once, 2 into 3 into remaining 2 into 3 into 5, 2 into 3 into 5, which is equal to 2 cube into 3 square into 5. From these examples, we can conclude to a common result to find HCF and LCM. See, HCF is equal to product of the smallest power of each common prime factor and the numbers. Here, the prime factorization of 6 is 2 into 3 and 20 is 2 square into 5. Therefore, the common factor is 2 and the least power of the common factor is 1. Therefore, HCF is equal to 2 raised to 1 or HCF is equal to 2. Here in the next example, the prime factorization of 12 is 2 square into 3 and 18 is equal to 2 into 3 square. The common factors are 2 and 3 and the least power or the smallest power of the power of 2 is 1 and the smallest power of 3 is 1. Therefore, HCF is equal to 2 raised to 1 into 3 raised to 1. That is product of the smallest power of each common prime factor. Here in this example, 24 is 2 raised to 3 into 3 and 180 is 2 square into 3 square into 5. So we have to first find the common factor 2 and 3 and next the smallest powers of common factor. Here the smallest power of 2 here is 2 square and smallest power of 3 is 3 raised to 1. Therefore 2 square into 3 raised to 1 is the HCF. Also, LCM equal to product of the greatest power of each prime factor involved. See, the factorization of 6 is 2 into 3 and 20 is 2 square into 5. In HCF, we considered only common prime factor, but here we take all the prime factor. Here the prime factors are 2, 3 and 5 and the greatest power of the each prime factor. Here the greatest power of 2 is 2 square and 3 is 3 raised to 1, 5 is 5 raised to 1. Therefore, LCM is equal to 2 square into 3 into 5. Next example, 12 is 2 square into 3 raised to 1 and 18 is 2 raised to 1 into 3 square. The prime factors are 2 and 3 and the greatest power is of 2 is 2 square and of 3 is 3 square. Therefore, LCM is equal to 2 square into 3 square. Next example, 24 is 2 cube into 3 and 180 is 2 square into 3 square into 5. Therefore, the prime factors involved are 2, 3 and 5. The greatest power of 2 is 2 cube here and the greatest power of 3 is 3 square here and 5 is 5 raised to 1. Therefore, LCM is equal to 2 cube into 3 square into 5. Also, we get HCF into LCM. See, here HCF is equal to 2, LCM is equal to 2 square into 3 into 5. HCF into LCM is equal to 2 into 2 square into 3 into 5. That is 2 into 2 square into 3 into 5, which is equal to 6 into 20. Here see, HCF is equal to 2 into 3, LCM is equal to 2 square into 3 square. HCF into LCM is equal to 2 into 3 into 2 square into 3 square. That is 2 into 3 into 3 square into 2 square, which is equal to 12 into 18. In general, we can verify that for any two positive integers a and b, HCF of ab into LCM of ab is equal to a into b. We can use this result to find the LCM of two positive integers if we already found the HCF of two positive integers. Then LCM of AB will be a into b divided by HCF of AB. We can see an example. Find the HCF of 96 and 404 by the prime factorization method. Hence, find their LCM. To find the HCF by prime factorization method, factorization of 96. 96 factorization we can see 96 is the least prime factor is 2, then 48, again 2, 24, to 12, to 6, to 3. Therefore, 96 is equal to 2 into 2 into 2 into 2 into 2 into 3. That is 2 raised to 5 into 3. And the factorization of 404. 404 is 2, 202, 2, 101. 101 is a prime. It is equal to 2 into 2 into 101. Here the common factors are 2, twice. Therefore, HCF is equal to 2 into 2 is equal to 4. To find the LCM, we have for any two positive integers, HCF of AB into LCM of AB is equal to A into B. Therefore, LCM of AB is equal to AB by HCF of AB. That is LCM of 96 and 404 is equal to 96 into 404 divided by HCF is equal to 4, which is equal to 9696. See another example. Find the HCF and LCM of 6, 27 and 120 using prime factorization method. To find HCF and LCM by prime factorization method, first we can see the prime factorization. Prime factorization of 6 is 2 into 3. 27 is 2 into 3 into 3. And 120 is 260, again 230, again 215, again 3, 5, which is equal to 2 into 2 into 2 into 3 into 5, which is equal to 2 cube into 3 into 5. Here 2 into 3 square. HCF is equal to product of the smallest power of the common prime factor. Here the common prime factors are 2 and 3. The smallest power of 2 is 2 raised to 1 and the smallest power of 3 is 3 raised to 1. Therefore, 2 into 3, which is equal to 6. And LCM is equal to product of greatest power of each prime factor. Here the prime factors are 2, 3 and 5. And the greatest power of 2 is 2 cube, of 3 is 3 square and of 5 is 5 raised to 1. Therefore, LCM is equal to 2 cube into 3 square into 5 raised to 1, which is equal to 360. For any two positive integers a and b, we see that HCF of AB into LCM of AB equal to a into b. But here HCF into LCM is equal to 2 into 3 into 2 cube into 3 square into 5. 2 into 3 into 2 cube into 3 square into 5, which is not equal to 6 into 27 into 120. So the product of three numbers are not equal to the product of their HCF and LCM. That result is applicable for only two numbers. We can see the exercises in the next video. Thank you for watching. If you find this video useful, please like, share and subscribe to this channel. Thank you.